Hi everyone, I'm Dorian, a PhD student at the IPPP, and I'm going to be giving you a very quick whistle-stop tour of how future experiments might be able to probe a particularly elegant solution of the Muon anomalous magnetic moment. So we're going to go in hot. We only have 20 minutes to do this, so going to have to be quick. So the recent results of the Fermilab National Laboratory have reinforced this tension with a standard model with the Muon anomalous magnetic moment, bringing the total tension when combined with the Berkeley National Lab result to around 4.2 sigma, which is almost that sweet 5 sigma. And what is this tension about? Well, in the standard model, when we look at the G factor of the Muon and we want to correct it for all of these different higher loop corrections, well, we need to consider things like QED interactions, weak interactions, and any kind of additional kind of hadronic processes that go on there. And when you add up all of those extra contributions to the Muon G factor, you get a little bit of a wobble outside of the number 2, which is fine. However, when we measure this G factor experimentally, which is done by looking at the difference between the precession frequencies of the muon's momentum vector as it goes around this big ring magnet and the precession frequency of its spin vector, you get something that doesn't agree with the standard model. And it's precisely this kind of 4.2 sigma tension that we're talking about here. And of course, this being a particularly juicy kind of fluctuation, well, not fluctuation necessarily, but this tension with the standard model that we hope for new physics isn't a fluctuation. There's obviously been a small zoo of different kinds of new physics models which have tried to explain this, including things like supersymmetry, 2 or 3 field extensions. We're going to consider just a very simple 1 field extension by adding this U1 gauge symmetry to the standard model. So here I've shown the BSM Lagrangian here that we're going to include. So just the important parts. So we've got our kinetic mixing, this epsilon X factor, which controls how the photon and the hidden photon, that we're going to call it, mix kinetically. We've got our gauge coupling here with the G, and we've got the mass of our new gauge field. Now, this X hasn't quite been rotated in the right mass basis, so it's still an X, but once we do all of these kinds of transformations, then this X becomes our hidden photon, the A prime. And this A prime, which should obviously couple to muons if you want to explain the muon anomalous magnetic moment, will have this kind of vertex here that will contribute to that correction. And that correction, the delta A mu, is going to be controlled by the gauge coupling here. Okay, so what kinds of U1 models will actually be able to explain this? Well, we definitely, as I say, wanted to couple to the muon, so an L mu gauge will definitely work. It's kind of the simplest thing that you can just sort of rattle out of your mind. And something like this will couple to the entirety of the second generation, the muon, the new mu. This will be important later because we want to not only probe the muon physics, but the muon neutrino physics, but it comes with a kind of string attached to it, which is this anomaly cancellation factor that we have to include if we want the sort of extension to be anomaly free. And we have to do that, we add these extra heavy fermionic field content. And that's a little bit ugly because not only do we have to add this extra hidden photon, but we have to add in sort of extra baggage. So one slightly more, a model that you think of a little bit outside the box is an L mu minus L tau instead, which also couples with the muon and the muon neutrino, but it also couples with the 3rd generation, our taus and our tau neutrinos. And this here is the main difference between the 2 models, and the fact that the mu minus tau doesn't actually require any additional field content. It kind of comes with no anomalies free. And this is looking particularly elegant to explain something like the muon anomalous magnetic moment. And we're going to take a bet on that elegance. Well, kind of two bets. The first bet is that we're going to assume that the G-2 of the muon is real. This tension is real. 4.2 sigma, almost 5 sigma, right? And we're going to assume as well that this L mu minus L tau model is what's actually responsible for it. And we're going to ask the following two questions. We're going to ask, can we experimentally observe the signatures that an L mu minus L tau will give at other experiments? And moreover, can we distinguish that model or the signatures from that model from the more generic L mu signature? Because they're looking like very, very similar models. And the key differences between these two models that we're going to come back to a couple of times is the fact that, firstly, the L mu minus L tau couples to the second and third generation. So an experiment that can distinguish between an L mu and L mu minus L tau should be sensitive to the third generation. And it's also the kinetic mixing that's crucially different as well. So for the L mu minus L tau, the kinetic mixing is actually governed by the mass scale of the tau, in which case you have a very set one specific value for your kinetic mixing of minus gx over 70. But for the generic L mu, because of that extra kind of fermionic content that we have to add to cancel all the anomalies, well then, if we want to just be kind of generic and phenomenological about it, then we can kind of let that mass scale run from, say, the electroweak scale to the gut scale. And we therefore get a range of the kinetic mixing values that are allowed. And this range will be between around minus gx over 10 and minus gx over 100. And very importantly as well, the kinetic mixing value of the L mu minus L tau model is within that bound. It's within the allowed set of values for the L mu. So we can kind of begin to see where some troubles might arise. So what we want to do is come up with this experimental strategy to actually tell if we can actually see this L mu minus L tau. And we're going to look at 3 different experiments. We're going to look at muon beam experiments, which are going to be very good at getting our coupling. We're going to be looking at spallation experiment, which are going to be good at discerning that value of the kinetic mixing. And then we'll be looking at direct detection experiments, which, although dark matter experiments, will actually prove very key to testing the third generation there and really discriminating between the two models. But before we start looking, we need to know where we're going to look. So this landscape here is the current L mu minus L tau, but also for our reasons, it's the same thing as the L mu allowed landscape here of where our coupling and mass can lie for this hidden photon. There's a lot going on here, all the grays, regions that are not allowed, and the important region here is this green region here, which is the coupling and mass band that our hidden photon can be in to explain within 2 sigma the muon anomalous magnetic moment that we're seeing here. And we're going to look at 4 representative kind of extreme first and fourth benchmark points there. Benchmark points that are going to be things that we might want to probe in the future experiments to actually see if these experiments can see these points in this landscape. And the important part here of these benchmark points is, they're roughly the same coupling, but their mass is quite different. So from BP1 to BP4, there's about an order of magnitude change there. And to test the experimental sensitivities, we're going to play what I've called the fitting game, which is where we're going to generate the data from our 4 benchmark points. We're going to cover the answer, pretend we don't know that it's from the L mu minus L tau. We're then going to fit, assuming that the model is either the L mu minus L tau or the L mu. And then we're going to hope that we can both retrieve the benchmark point that we started with, and we can also get some model discrimination out of it. So let's go. So first of all, we have our muon beams, which work by sending a muon or muon beams hurtling towards this target. Some kinetic mixing with the standard model photon, that epsilon x, gives us the production of the A prime through Bremsstrahlung radiation. That A prime is going to decay. It can decay principally into 2 channels, either into 2 muons or 2 neutrinos through an invisible kind of decay. But because within the G-2 solution, the mass of the A prime is less than twice the mass of the muon, we only have to worry about the invisible decay. And these experiments will look at this missing energy signature to give us a spectrum for kind of what went on within the beam that we couldn't see. How many A prime events happened to account for that missing energy. And we'll look at NA's, the data that we've kind of generated is from Na64 mu. We're going to generate this data. It's just an extension of its electron cousin. It's got these calorimeters, which detect that missing energy through the detector. And it's characterized by this lead target that it has over here. The number of muons that are going to be on this target, the length of the target, and this detector length over here. We can see that IA prime here enters the detector, and all the invisible decay products kind of escape, and then all we measure is this missing energy over here. Now the signal is going to be governed by this top equation over here. This is how we get our spectrum for this experiment. We've got our A prime to invisible branching ratio, which is going to be 1, as we said, because it has to decay invisibly for this solution. And importantly, it's got the production cross-section here of the A prime through the Bremsstrahlung process. And when we look at that cross-section, we see that it's proportional to a complicated function of the mass and gx squared and no kinetic mixing whatsoever. Now, this is an oh no, because the gauge coupling could be either from the L mu or the L mu minus L tau. And because we're only looking at the muon, which both of them couple to, and there's no sensitivity to the kinetic mixing, there's no way to discern the two models. So we can definitely play the fitting game and get an idea of the coupling of the data that we're generating, but there's no way that we can actually differentiate between the two models. So when we do play the fitting game, this is the kind of picture that we get. So we get some nice 1 and 2 sigma closed contours here around the benchmark points. And something that happens with these muon beam experiments is that actually the higher in mass you go, the better the signal you get. And there are different characteristics that come about from having higher signals. And for the lower mass benchmark points, VPs 1 through 3, there's quite a wide range of mass, but for all of them, the coupling is pretty well constrained, which is why they're the coupling capturer. So the Na64 mu and other muon beam experiments like it will be able to give us the gauge coupling piece of the puzzle. It also has some sensitivity to the mass of the hidden photon, which is better for higher masses, but very importantly, you can't actually discriminate between an L mu minus L tau and a more generic L mu. If only we had sensitivity to the kinetic mixing. And this is exactly where spallation experiments come in. So spallation experiments work by protons colliding with a target. That collision produces pions, which then decay into muon neutrinos and an anti-muon. The anti-muon can then decay to a positron, an electron neutrino, and an anti-muon neutrino. And these neutrinos then coherently, elastically scatter with nuclei through Sevens physics. And the spectrum of that Sevens physics tells us about, or the spectrum in the distribution of events of the recoil energy of the nuclei tells us about the Sevens physics here. And there's a sort of smorgasbord of different spallation experiments that have been projected. I'm not going to go into all of them really, but this is a sort of at a glance view of the experiments that we can look at when we do this. And there are all these different places: Oak Ridge, the European spallation source, and the Los Alamos National Lab here. And they differ with all of their configurations, but they're all measuring Sevens. Now, this is the equation that's going to govern the signal that we're going to get from this Sevens. Here, importantly, we have the scattering physics here. This is where we're going to meet our A prime. There's the experimental neutrino flux that we get over here. This is from the neutrinos that are produced in the pion decay. There's an efficiency function here, which tells us how good or bad we are at getting the signal for a particular nuclear recoil energy. There's the binning of the spectrum, and very importantly, there's a flavor sum with all the neutrinos that we have available to us. And we only have electron neutrinos, which we don't care about because they're not affected, and the muon neutrino, so we don't have any tau neutrinos. When we look at the cross-section, is proportional to a standard model term, an interference term, which is greater than 0, and a strictly positive BSM term. Now, the interesting thing about the interference term, which is what's going to govern the kind of signal that we're going to get, is this overall sign that we're going to see with it. Now, the gauge coupling is positive. The interference term here is positive. The kinetic mixing term we know is negative. So it's now going to be governed by the charge of the neutrino as per the gauge group. So for the muon neutrino, this charge is positive 1, whereas for the tau neutrino, this charge is negative 1. And what this means is that for the muon neutrino, we're going to get positive number times positive number times positive number times a negative number here in the kinetic mixing. So we're going to get a net overall negative interference. So we're going to expect a deficit of events with respect to the standard model. And what we don't get, but what is very interesting, is that if we had tau neutrinos, that charge is flipped, and instead we'd expect a positive interference term, and we would get an excess. But we don't get anything like that here because we don't have any tau neutrinos. And just as a summary of how the fitting game is going to work here, importantly, this cross-section is dependent on the product of the coupling and the kinetic mixing term. So we do have sensitivity to the kinetic mixing term, which Na64 mu didn't have. And for an L mu, that means that we have to assume a value for the kinetic mixing, which, if you remember, is not fixed. And say that we assume the wrong value for that kinetic mixing, say minus gx over 10 instead of minus gx over 70. Well, then when we fit, we're going to expect that the coupling will fit lower to compensate for that because of that product kind of dependence. But we know that Na64 mu already has stakes on that coupling. So we know that there's going to be some tension. And if we give it the wrong kinetic mixing, we do indeed see this tension. So here we have the Na64 mu regions, the blue regions, and we also have this sort of more warmer tones, which is where oscillation experiments would fit. And we can see a definite tension here, with these here being upper bounds. You can see that with these upper bounds, it entirely excludes the region that Na64 mu had. So if we instead give it the right kinetic mixing, we see that this tension disappears. So what we can do, as a sort of a summary here, is that if we want to fit the coupling, we have to assume a value of that kinetic mixing, and we have to play this game with this lever to make sure that when we do fit, that everything has no tension and that we kind of retrieve something that kind of corroborates with the two experiments and we add them together. So as a quick kind of overview of the strategy that we can have here, we can do our muon beam experiments, get our coupling. We can do oscillation experiments, get our kinetic mixing, and then we can ask, well, does the data corroborate with a value of gx, of an absolute value of gx over 70? If it doesn't, then we know that it can't be L mu minus L tau because that is the value that L mu minus L tau must have. So then we know that it's an L mu. If it does, and an L mu minus L tau could have the same values, then we're in a bit of a problem situation because there's no way that these two experiments have any kind of other sensitivity to a difference. And the only other difference that we can really probe here is the tau physics. And this is where direct detection comes in. So, usually we think of direct detectors as dark matter detectors, and that's because they are dark matter detectors, but they're beginning to branch out into solar neutrinos as the sensitivities drop lower and lower. So here we can see that these xenon dark matter detectors are beginning to cut through this orange kind of orange-yellow region, which is where our solar neutrinos kind of live here. And this is very bad for dark matter detection because it's an irreducible background. It's very good for neutrino detection, which is what we're interested in, because it then becomes an irreducible signal. And we've got lots of different experiments here that we can choose from, but previous work has showed us that it's the liquid xenon experiments that might be able to make the most important kind of difference here in the G-2 landscape. So this here is the 90% upper bounds that we can draw with Darwin and LZ, which are both liquid xenon experiments in the L mu minus L tau landscape by looking at that signal. So we're going to focus on Darwin because it's very big. It's the one that gives us the most promise. It's 200 ton-year exposure. It has this light to charge signal that can be used to tell if we have a nuclear recoil or what's generally a background electron recoil. And it generally has a very high threshold in energy. There is precedent, which we need to get to a 1 keV recoil threshold. And we need this low energy threshold because this is where our solar neutrinos are going to start coming in. So we need to get as many of them as possible. And in terms of the physics here, it's exactly the same. It's sevens, right? It's exactly the same as our spallation experiment. Only now our sum has that tau included. We now have a solar neutrino flux here, or solar neutrinos are born electron neutrinos. And we also have this transition probability as our electron neutrino becomes another flavor of neutrino as it oscillates all the way from the sun to the earth. And the probabilities here show that, so these are our electron neutrinos and how their probabilities evolve with energy. And here are our tau neutrinos here and our mu neutrinos. And the important thing here is that our mu neutrinos are always losing. They never ever become any greater than the number of tau neutrinos that we might get here on Earth. So what does this all mean? Well, if you remember, the tau neutrino is actually going to have a sign flip for the charge, which is going to give us positive interference instead of negative interference. And because we have more tau neutrinos that we're going to see than mu neutrinos, that means that positive interference is going to win out with the L mu minus L tau, meaning that if we do have an L mu minus L tau, we're going to see an excess. If we have an L mu, the taus are out of the picture and we'll see a deficit, and that's the killer. So for direct detection, if we look at our nuclear recoils and we see an excess, we know it's an L mu minus L tau. If we see a deficit, we know it's an L mu, and that's the killer. And when we play the fitting game one last time, this is the kind of picture that we have. And now we're just going to say that this is an L mu minus L tau, because that's the underlying model that we've picked, and it's definitely an excess now. And we see that all of the experiments kind of corroborate here. They all kind of link in, and you can see that there's this overlap region over here as well for the second benchmark point. The third benchmark point and fourth benchmark points are more difficult to probe in sevens, but nonetheless, it really does cut the region off. And everyone is sort of playing their part in giving you a piece of their own puzzle. So dark matter direct detectors are sensitive to that coupling, just like spallation experiments are, but they're also sensitive to the new taus, which the other experiments weren't. If we modify Darwin to a 1 keV threshold, then we could discover an excess in L mu minus L tau or the deficit in L mu in sevens. And just like the other experiments give us pieces of the puzzle, Darwin could tell us what puzzle we're actually solving. So I'll leave these conclusions here, and also this very nice kind of strategy that we can follow here to get to a Nobel Prize. So we can get to our muon beam, get our coupling. We then go to our spallation experiments. We've got our kinetic mixing. If we find a value that is not Gx over 70, then we know we have an L mu. That's kind of part of the problem solved. If we do have Gx over 70, well, then we have to go to Darwin. And when we measure our solar sevens, we then will see either an excess or a deficit. If we see a deficit, again, we know it's an L mu, but if we see an excess, we can definitely tell that it's an L mu minus L tau. So hopefully this will bring us one step closer to getting to that Nobel Prize. Thank you very much.